Today we will be seeing about the working principle of single-phase induction motor and its types. Okay, this is the single-phase induction motor which is present in your houses and in most of the industries. Okay, this single-phase induction motor has a major disadvantage. The disadvantage is it cannot start by its own. Okay, you can see for an example. Okay, in our houses you will be having fan. In some cases, the fan may not start. Okay, if you turn on the switch, the fan may not start. In that time, you can rotate the fan by your hand. At that time, the fan will start and it will start running. Okay, so there is a starting problem in induction motors, particularly in single phase induction motor. It is not in three phase induction motor. Okay, so why this problem occurs in single phase induction motor and how we are rectifying the starting of single phase induction motor. This is the topic we are going to see today. After that, we are going to see about the types of induction motors available. Okay, so you all know there are stator and rotor. Okay, stator is the part which will not rotate, and the rotor is the part which is going to rotate. Okay, in stator you will be having a single phase winding in case of single phase induction motor. In three phase induction motor you will be having three phase winding. Okay, the rotor, there are two types of rotors. One is squirrel cage rotor, another one is slip ring induction rotor. Okay, so in this figure you are seeing a single phase induction motor construction. Here in this rotor you will be having a single phase winding. Sorry, in the stator you will be having a single phase winding. Okay, this winding you will be having two windings. One is main winding and another one is starting winding. Okay, the rotor will be a squirrel cage rotor. Okay, and this is the air gap. Air gap is nothing but the gap between the stationary part and the rotating rotor. Okay, so this is the air gap. So why we need a secondary winding, that is known as starting winding? This we need to see. In case of single phase machine, you will be having a single phase winding. Okay, if you take a rotor stator over here, in the stator you will be having windings. Okay, you will be having windings. Okay. These windings will be connected to a single phase supply. Okay. Single phase supply is provided into the stator of the single phase induction motor. When you provide a single phase supply, the voltage present in the supply will be like this. Okay, this is the time and this is the voltage. Okay, this will be the minus voltage and this will be the plus voltage. Similarly, the current associated with this will be like this. Okay, so we will be having current also. Okay, minus I. Then you will be having another one component, which is nothing but the flux, magnetic flux. Okay, magnetic flux which is produced by the winding. If you give the supply into the induction motor, at once the magnetic flux of lines is produced. Okay, this will become an electromagnet. Okay, this stator will become an electromagnet and it will produce a magnetic flux of lines. Okay, this is the flux of lines produced inside it. Okay, this is for single phase induction motor. Okay, when you compared with the three phase induction motor, what happens? This is the stator. Okay, you will be having a three phase winding. Okay, Here you will be having the R phase, then you will be having the Y phase, okay. Then here you will be having the B phase, okay. Sorry, Y phase and B phase. You will be having three phases, okay. These three phases are connected to a three-phase supply, okay. R phase, Y phase, and B phase, okay. These three phases are being connected to the supply, okay. This one will be the R phase, this one will be the, sorry, this one will be Y phase, okay. This one will be Y phase, this one will be R phase, and this one will be B phase, okay. This will be connected to the three-phase supply. Once the three-phase supply is connected, the flux, that is the magnetic flux produced in the rotor, will be in such a way that the flux will be rotating in nature. Okay, this flux present will start to rotate inside the rotor. Okay, so a rotating magnetic flux is being produced in the three-phase induction motor because you are providing three phases R, Y, and B. Okay, you are providing three phases, so three-phase flux is produced, and this three-phase flux has a tendency to rotate inside the rotor. So this rotating magnetic flux will help us to run the rotor or to start the rotor. Okay, this is for three phase. When you come back to the single phase induction motor, you can see there is only one flux produced, okay, and this flux is rotating, okay. This flux is also rotating, but there is only one single flux is produced because you are using a single phase supply. So in this case, what happens here is the flux produced, that is the flux, this is the flux, okay, pi m, okay, this is the flux pi m minus pi m, maximum flux, okay. This is the pi m, and this is, and this one is minus pi m, okay. These fluxes created inside the rotor will be like this, okay. Pi m by 2, and another one is pi m by 2. So the sinusoidal flux which is created inside the rotor with the help of a single phase supply will have two components. One is A component and another one is B component. So these two components are in such a way that it will be half of the maximum flux pi m. Okay, so what happens here is the flux which is being created will be the half of the maximum flux. So what happens, the the torque, that is the torque produced in the motor, tends to rotate in the clockwise direction by this component A. Whereas in the second part, you can see the component B starts to move the rotor in the clockwise direction, whether the component A starts to rotor in the anti-clockwise direction, here and here. So what happens is the rotor tries to rotate in the clockwise direction first. After that, the rotor will try to rotate in the anti-clockwise direction next. So what happens is the rotor cannot rotate because the component A starts to try to make the rotor in A direction, whereas the component B tries to rotate the rotor in the anti-clockwise direction. So the rotor will stop and it cannot rotate, and it will be in the in stationary position. Okay, it will not rotate. So this theory is known as double field revolving theory. So Due to this, the single phase induction motor cannot start. Okay, but when you make the motor to rotate by your hand, you try to rotate the motor by your hand in the anti-clockwise direction. What happens is you are giving a extra force. You are giving extra force and trying to overcome this B component. Okay, the B component is trying to move in this direction. Okay, but you are providing more force in to the A component by your hand, and this A component has more power than the B component. So what happens is at the initial stage when you start to run the motor with your hand, it will be pushed by the A component as well as your hand. So this component A has more torque and more power and start to rotate in this direction because the B component is lesser. So once it starts to rotate in this direction, the A component makes the rotation again and again, and the rotor will attain its full speed. So this is the concept of double field revolving theory. Okay. Now this is the graph representing the double field revolving theory. Okay. Here you can see there are two components. One is the A component and another one is the B component. Okay. These are the two components. You can see the A component is trying to move the rotor in the clockwise direction, whereas the B component is trying to move the rotor in the anti-clockwise direction. So the resultant vector will stop at the one position. Okay, so at this position the motor cannot rotate because the two torques, that is the torque in the anti-clockwise direction and the torque produced in the clockwise direction are same and equal. So the net torque produced in the rotor is 0 or it will be represented as 1, so it cannot rotate. So next we are moving to the types of single phase induction motor. So how we are rotating the motor. So we can see the first type is we are using is split phase induction motor. Okay, split phase induction motor. In split phase induction motor, you will be having two windings. One is main winding and another one is secondary winding, or otherwise known as starting winding. Okay, so there are two windings. You will be having a switch and a resistance. This switch is known as centrifugal switch. Okay, so when you supply a single phase supply into this motor, what happens is the main winding will create a flux. Okay, the main winding will create a flux. Okay, this is the main winding flux. Okay, take it as phi m. Okay, next you are having the starting winding. Okay, you are having the starting winding. The starting winding is connected with the resistance. Since the resistance is connected with the starting winding, the current flowing in this branch will have a negative shift in power factor. Okay, so what happens is the flux created by the starting winding will be like this. Okay, so what happens is there is a phase difference. See, there is a phase difference. Okay, there is a phase difference. This phase difference will help us to start the rotor in this direction. Okay, once the motor starts to rotate, the rotor will attain the speed at a speed which is compared with the centrifugal switch cutoff speed. Then the switch will open. Okay, if the motor rotates at a faster rate due to centrifugal force, the switch will lift up and the starting winding will cut off. Okay, the current flowing in the starting winding will cut off. Okay, this is the representation of the centrifugal switch. Okay, you can see this is the starting main winding, and here is the starting winding, and this starting winding is connected to the centrifugal switch. Once the speed is attained, the switch will return back and the supply get opens. Okay, so the motor will rotate with the help of main winding. Okay, this is the phasor diagram. Okay, here you can see the representation of the starting winding current, which is represented as IS, and the magnetic main winding current, which is represented as IM. These two currents lag by an angle of alpha. So the total current which is produced or which is given inside the motor as a load current is represented as I. So the vector sum of the two currents, that is the starting current as well as the main current, will give you the load current I. So the difference between the voltage V and the total current input into the motor IL is represented by pi flux, that is the pi, and this pi is known as the power factor and it is represented as cos pi. Okay. The next type of winding, that is the next type of motor, is the capacitor start motor. Okay. In case of capacitor start motor, you will be providing a single phase supply over here. Okay, with respect to time axis, and this is the main winding flux created. So this will be the flux. Okay, and this will be the minus flux. And here you can see we are having a starting winding. Okay, we are having a starting winding. You are having a capacitor with the centrifugal switch. Okay, so the at the initial condition, when this motor is rushed, the current will flow into the starting winding and into the capacitor and into the switch, and it will return back. So at the initial stage, the current which is flowing into the starting winding is denoted as IS. Since the current is flowing in the winding, a flux will be produced in the winding. This flux is known as starting winding flux. Okay. So this flux will be produced because of the capacitor as well as the inductance present in the starting winding. You know, since the capacitor is connected in an alternating supply, the current will lead the voltage. So the flux produced here will also lead the flux which is produced by the main winding. So this is the flux produced by the starting winding, and this one is the flux which is produced by the main winding. So there are two fluxes. One is the main flux phi and another one is the starting winding flux phi. So these two fluxes interact in the rotor and make the rotor to run in the clockwise direction. So when you come to the phasor diagram, you can see the starting winding flux is leading because of capacitor. You can see the capacitor is connected. So the starting winding flux is leading and the main winding flux, that is the current, is lagging with respect to voltage. So this is the voltage line. With respect to voltage line, the starting winding flux is leading, whereas the main winding flux is lagging. So the vector sum between the starting winding flux and the main winding flux gives you the total current I which is produced in the total amount of current which is given as input into the single phase motor. So this is a capacitor start motor. Next, we are going to see about the capacitor run motor. Okay, in capacitor run motor you will be having a fixed capacitor and you will not having a centrifugal switch. You will be having a starting winding, you will be having a main winding, etc. Okay, in this type of motor what happens is the starting winding and the capacitor will not be disconnected because there is no centrifugal switch. But in case of capacitor start motor, you are having a centrifugal switch. Once the rotor attains its maximum speed, which is equivalent to the centrifugal liftoff speed, at once the switch will open. Okay, the switch will open and the current which is flowing into the starting winding gets cancelled, will be stopped. So the motor will run only in the main winding. But in case of permanent capacitor run motor, there is no centrifugal switch. So the current in the starting winding will always be present as well as the main winding is always be present. But here you can see the only difference is the main winding flux has no capacitance, whereas the starting winding flux, this one, has capacitance. Since it has a capacitance, the flux will lead. So there is a resultant. This resultant flux, that is the phase difference between the two fluxes. That is the starting winding flux and the main winding flux as a phase difference. And this phase difference flux will be induced in the rotor, and this will make the permanent capacitor run motor to rotate in the clockwise direction. When we are coming to the phasor diagram, you can see the starting winding. Because of capacitance, the starting winding flux is leading. So the current is leading. Okay, you can see the current is leading. This is the starting current. Similarly, you are having the main winding current, which is lagging, because here you will be only having the pure inductance L, so it is lagging with respect to voltage. So when you draw a phasor diagram, you can have a vector sum up, then you will get the total current I which is flowing in the motor as a load current, which is IL, or which will be equivalent to I. And this one is the last, this is the next type of motor. Here you can see this one is the capacitor start, capacitor run motor. Here you will be having two capacitors, C1 and C2. Okay, there are two capacitors, and here you are having a centrifugal switch. One capacitor is connected always in the line, whereas the other capacitor will be connected and it will be disconnected when the centrifugal switch is lift off, when the maximum speed of the rotor is attained. So this is another one type, and you are having another one type of motor also, which is known as a shaded pole induction motor. In shaded pole induction motor, in the stator you will be having a copper band over here. Okay, like this. You can see there will be copper band in the rotors. Okay, here also you see there will be a copper band. What happens is this copper band will produce more flux, okay, whereas in this region very less amount of flux is created. Okay. But in this region more amount of flux and dense amount of flux is created. So due to this uh, difference in creation of flux, that is the intensity, the difference in intensity of creation of flux. Here you will be getting more amount of flux of lines. Okay. Here you will be getting only few lines. Similarly here also. Okay. Here you will be getting only few lines. Okay. So this difference in magnetic flux created by the shading band. This shading band, this one is nothing but the copper band. Okay, this is a copper ring. Okay. Due to this difference in intensity of flux, the motor will start to rotate. So we have discussed about the types of single phase induction motor and also the double field revolving theory, which is being present in the single phase induction motor and which is stopping the motor from start. So we are having several types of motor to start the motor. Okay. Uh, with this we can conclude the class.